This instructional video is on the note sheet 6.6a Vertex Form. So Vertex Form requires us algebraically to complete the square so that we could put the problem into this form. This form gives us A, H, and K, which in 6.6b we'll learn their graphical implications. But for now, we're just going to focus on putting a quadratic in this form by completing the square. Once in this form, as you can see here written in blue, you could get the H and K values, which written down here give you the vertex right away. So you don't have to go opposite of B over 2A and then substitute into the function to find the y coordinate of the vertex. It's already there, and that's one of the powers of vertex form. Also, whatever the x coordinate is of the vertex, that's the x value for your equation for the axis of symmetry, and it must always be an equation like if h is equal to 5, then x equals 5 would represent that vertical line. And for now, please note that in the vertex form, this is a minus, so really h is just by itself, like you can see here. So really you take the opposite of what you see. So if we had vertex form of x plus 3, then that really means from this minus here that it's x minus a negative 3. So that's why h is just that negative 3. But we'll learn in 6.6b why this is the case. For now, I want to go over a couple examples of how you complete the square so that you could put a function in vertex form. So let's go ahead and quickly review completing the square. In the past, we put the 11 on the other side, the constant. We took half of the linear coefficient, squared it, and added that to both sides. And then you can take the positive and negative square root of both sides and solve using completing the square for this quadratic equation. But now let's go through the same problem, but let's pretend that we can't go on the left-hand side of the equals. Because when we set this equal to a function in a little bit, we will want to avoid putting anything on that side. Not that we can't, but we would just have to undo it later, and why would we want to do that? So the first thing is to push the constant farther to the right. And now we do half b squared, etc. Now, instead of putting the 9 on the left-hand side to balance the equation, we could balance the equation by what we put in, we take out. So that is what we'll call adding 0. And so what we do next is half of the 6 was 3, and then we collect the positive 11 and the negative 9 for a positive 2. And if you remember last time, this side was negative 2, so then it's just like moving that over in the end. So let's look at a couple examples. So we want to write in vertex form, find the vertex and the equation for the axis of symmetry. So in this example, which is the second from the note sheet, I'm sorry, the first one from the note sheet, usually we would throw the negative 12 to the other side as a positive 12, but we now have a function here, so we want to keep that just the dependent variable by itself the whole time and not have anything over there with it. So instead, I'm just going to take this negative 12 and move it farther to the right so I can make a little space here. Fortunately, I'm running out of room, so let me rewrite that. So I push the constant farther to the right, and now I take half b squared, etc. So that's 8 squared is 64. That wasn't there originally, so then I have to subtract it out. So together they make 0. So I didn't change the value of the function, only its form, because now out of these three terms, I could complete the square because the factors of 64 that sum to 16 are 8 and 8. I set it twice, write it once with an exponent of 2. And then over here, I could take that to be negative 76 for part A vertex form. Now, inner invert, so H is negative 8. Outer original, K is negative 76. So the vertex is negative 8 comma negative 76. And so the equation for the axis of symmetry is x equals the x-coordinate of the vertex, x equals negative 8. In this example, the leading coefficient was 1. So now, let's take a look at what happens when you have a leading coefficient. And this will be the third example from the note sheet. Leading coefficient that's different than positive 1. The story's the same. You still push the constant farther to the right. What we'll also do, however, is factor out the leading coefficient from the terms that have a copy of x, never involving the constant. So we factor out the leading coefficient. So dividing out negative 2 makes 16 a negative 8x. Leave a little space, and then that constant plus 17 goes farther to the right. So now we take half of this, square it. Negative 4 quantity squared is 16. But here is the trick. Remember, the big picture is that you're multiplying this through on the outside, so even though you just put in a plus 16, it's really a negative 2 times 16 for negative 32 that you need to balance. So add 0, and so that's why it's going to be a plus 32 on the outside. And so this sign and this sign will always be opposite to one another because squaring a real number is always positive. And that's completing the square for a function, so it's completing the square on one side of an equal sign. So to finish this up in vertex form, factors of 16 that sum to negative 8 are negative 4, set it twice, write it once with an exponent of 2, or in other words, whatever half of the linear coefficient. That gives you this. And then out here, that sums to positive 49. That's vertex form. The vertex, inner invert. So this here gives you 4, and this here gives you the 49. And then for the equation of the axis of symmetry, it's an equation x equals the x-coordinate of the vertex.